things about this is that these two molecules are solids or liquids when they're kept in a vessel under a little bit of pressure. All these are essentially gases, especially when they're hot and you're done. That's really what you want in an explosive. You need an explosive for your rocket. You need something that's going to rapidly turn from a small molecule object into a very hot, energetic gas. Remember the gas laws that you learned in chemistry. The volume that a gas takes up. What was that law? Anyone in calculus? Remember that formula? P equals nRT. So the volume is going to be proportional to the temperature. So something that's going to be energetic and hot. It's also linked to the number of atoms. The actual shape of that has a little to do with how much volume that it takes up. Hot, energetic, liquid gas expand to a very high volume quickly. If you do that in a rocket, though, you shoot everything out at once. Incredibly impressive structure, and it's all liquid hydrogen and oxygen tanks, and it's miles of Fleming what looks like. You combine these in the different stages that took this as a group of people to the moon, and it would have been much more efficient weight-wise and size-wise to use a chemical rocket at that point. But once you light the firecracker, you're not turning it off in a chemical rocket. So there's this ability to afford a manned mission. Only recently, chemical rockets become reliable enough where NASA now puts manned space missions on chemical rockets. The shuttle, of course, had that combination of chemical boosters, solid rocket boosters on the side, and liquid fuel in the main tank for that stage. And so, the moral of the story is you take something that's very compact, a liquid or a solid fuel, and you make a hot gas as a propellant. And this is how you get into space. And it's also how you do basic station-keeping operations when you're in space. Now, however, once you're in space, you do have a few alternatives to solid rocket fuel. One of the ones that's being used more and more nowadays is the concept of an ion rocket. And to understand this, to understand something that is kind of a dying art nowadays, the science behind ions and charge fields and things. When I first got to Georgia Tech in 2003, I was teaching undergraduate electromagnetics, and that fall, I had a nice-sized class of 50-plus students, and I prepared a whole lecture with really nice-looking animations and explaining how a cathode ray tube works, right? Because it's a beautiful electromagnetic problem. Students that are learning static electrostatics and magnetostatics, it's a wonderful illustration that they use every day, right? So how does the cathode ray tube work? You have this nice vacuum tube. The cathode is over here. This is the thing that's emitting the electrons. You have a screen, a mesh screen here. This is your anode. And a very high DC voltage applied between the two. So this is actually applied to a little the metal that has a annulus here. We're going to attempt to heat up the cathode. The electrons are getting ready to jump off. Really hot. They jump off here, and of course, the electric field points. We're going to get the polarity right. Let's see. Electric field should point this way. Positive to negative. Why? Because the fields, in this case, are going to point this way, and the electrons are going up the electric field because they're negatively charged. So they jump off through here. There's usually a little cylinder that I'll draw a cross-section here, and the cylinder is usually held at a very high voltage difference as well, which causes some electrostatic lensing, so the electrons that come through here actually focus down to a beam. And of course there's some steering magnets here, both in vertical and horizontal direction that causes the beam to sweep around. This little plate you can modulate with the data signal, so you can control the intensity of the beam, and voila! You have black and white colors. State-of-the-art performance, right? That's how I would teach this for a second. They were using CRTs in 2003, and students were so happy. We go home and they said, oh wow, I was at a dinner table and I explained to my parents how the television worked, and they thought they were getting such a good deal sending their children to Georgia Tech. And then, 2 years later, I gave the same lecture, everybody was asleep. Why? Because they were all using flat screens. It's like the fastest uptake for technology. So there's a lesson for you. You should listen really. One lesson, don't get too wet into your ideas or your technology because it's going to change and over. It only takes a few years for something to get completely obsolete, no matter how cool it is. The upside, though, is that first principles are first principles, no matter what they are. We just take this device. So we cut off the G, the screen, and we reverse the polarity. We have an ion fire. A source of ions, a propellant source. You heat it up and you remove some electrons, and you have a handy positive ion and some electrons that are kind of floating around. And if you reverse the polarity, you're going to accelerate the ions in a particular direction. Come this way. And then you're going to complete the circuit by letting the electrons jump back into the ions as they're accelerated out into electrostatic field here. And of course you do that because if you didn't have that circuit closure, you have this negative charge building up on your spacecraft, and eventually they would electrostatically attract all of those positive ions that were flowing out the back of your slowly lose plus ineffectiveness in your ion drive. Now, what's the nice thing about this? Why do we use this as an alternative? Here's the problem. Ion drives are terrible at providing thrust. An arrangement like this typically only provides 1/50th of a pound of thrust. Or 1/50th of a pound. Well, in space, where you don't have to overcome air resistance, it's actually pretty decent, provided you can turn it on for a long time. You turn it on, you let it go for a long time, that 1/50th of a pound, if it's turning continuously for days or even weeks, will integrate to a very large acceleration. What's more, you achieve that acceleration with relatively little fuel. Because in this case, the fuel, the thing that you make the positive ions with, is really being only used as the momentum, the propellant. It's not actually being used as a source of energy. In the rocket, the fuel has to do both. And therefore, that limits you your options. You have to have these energetic reactions and something that's going to make hot gases come out of your nose. In this case, the actual power, the energy for generating that momentum is electrical in nature. That's where you're going from electricity to the mechanical form of energy, kinetic energy coming out of that. So if you come up with the real trick for the ion drive, you come up with really dense liquid fuel that ionizes easily. And if you can do that, then you're pretty much able to take some fuels out, some acid fuels. Using the periodic table. So for this, we're going to go switch to the document camera, and you can actually orient it in the proper direction. We're going to do chemistry. Here you see the target. Here's the periodic table. surface atmosphere beyond the sea. That sort of thing. But again, Julie, argon is very acidificated in the air, and it's a little bit heavier than the krypton. Very heavy, it's on the order of 83. That's what it is in ion drive because it's particularly heavy. And then there's a real nice one, xenon, a little more rare than these other elements, but in that, it makes a very good compound. It's 131. It's atomic weight. It is something biological reasons why that's difficult to carry in a rocket. So they're usually use that one as a propellant. Highly radioactive, because it's going to land in some other particle naturally. Although there seems to be an abundant source for engagement for some reason. So these are headed xenon and particularly well for xenon equipment. You don't want to use a share of propellants for ion drives. And what's the issue with the space with it? When you turn it on, and any of the particularly useful devices for However, when you look at the entire package, the size and weight of the drive, even though they take many days to get that spacecraft into stationary Earth orbit, the ion drive tends to be cheaper in itself to launch it into space than the stage that would conventional orbit would take it all the way to higher Earth orbit. So, those are candidates for really higher Earth orbit, and also for deep space missions as well, because you can charge it for a long period of time. You're going to be spending years to go into outer space to and I actually think the very first space mission in the 90s that used an ion drive was a NASA mission to the asteroid belt, where you were going. It's going to take several years to get there anyway. We're not sure anything. We're either a little quicker using minimal mass. So, we have to have some research at Georgia Tech, several faculty members that are doing some interesting research in ion drives. See that used more and more. Blurring the lines here. There are launch systems, which we always use for rocket fuel. And we have some of the same types of techniques, as well as ion drives and a larger class of rocket fuel systems for orbital control systems, that is, controlling the orbit once you get into space, placing it into a final orbit, and then maintaining that orbit doing the minor corrections that are required. And then there's also attitude control systems, which also have to do with positions, but it's a different ball of wax. So you can imagine, I launch the satellite, it's in stable orbit, I can fire my little thrusters to quickly adjust it and keep it in the orbit that I desire. But there's a whole dimension of orientation that we have an interest. And this is important, especially if that satellite has a communications dish or directional antenna that must point to a certain spot when the Earth maintain a radio link, or it's doing some sort of measurement with a camera of the surface of the Earth, some sort of observation. How do you maintain the orientation of a satellite for this type of thing? Okay. So, there's raw. A couple different types of spacecraft. Spacecraft come in a lot of different shapes and sizes. But generally speaking, there are a couple basic body types. And a lot of it has to do with how the attitude control for the spacecraft works. How do you stabilize the spacecraft in space? And so one of the simplest ways to do that is to make a trunk-shaped satellite. You plaster it with solar panels, and when you launch this from your rocket, when you deploy this payload, you give it a twist, you spin it. And these are colloquially known as spinners in the satellite industry, or if you want to be official, single-axis stabilized. Because basically, when you spin this imparts angular momentum along an axis, and this satellite will hang there, and by definition of angular momentum, will stay oriented along there, not unlike a gyroscope, as it revolves around the Earth. And so you don't really need a lot of fancy attitude control systems once you've done that. It is good to have maybe some little thrusters on the side so that you can energize spin up or spin, depending on how your spacecraft is performing. And one of the issues here, there are a couple issues. You greatly simplify the attitude control when you build a drum-shaped satellite like this and spin it in orbit. However, there are a few things that you have to be aware of. First of all, you need power. And so the power source of choice in space, especially for Earth-based satellites, is almost always solar cells for their longevity, amount of power that they bring out. We'll get into power spacecraft systems in a few minutes. But you usually plaster this thing with solar cells so that as this thing spins around, one side of it is always facing towards the sun. Now, it's not the best use of solar cells because if you do a quick calculation, only one side of the drum is facing the sun, and a lot of the facets of that side, they're not optimally oriented. They're kind of off to the side, so they're not collecting maximum incidence effect. What you find is that if you were to compare the output of a drum-shaped arrangement of solar cells to a regular solar cells that were flared out into a flashy area, you're only getting about a third of the power from the optimally pointed flat solar panels. So one of the downsides is that these solar cells are only about one-third efficient. But they don't require any fancy pointing actuation in order to operate. They're always going to be pointing towards the sun. And then the next challenge that you have is that, okay, you've stabilized the orientation of your spacecraft, but you now have a platform that's moving, so how do you do communications? Well, a typical way is to take either the direct communications antenna or a reflector off there, and you de-spin it. Meaning that this is now connected to a rotary mount, and you de-spin it at the same rate that you start the satellite, so that the reflector is always facing towards Earth. Now, how do you always make sure that it's facing towards Earth? You have to equip your satellite with sensing systems. Quite often, an infrared type sensor is used to actuate the antenna to figure out which side the Earth is on. The Earth is relatively high compared to the blackness of space, so it's relatively easy to build a sensor to actuate the position of the Earth. And so this thing is spinning around, the reflector is G-spun, and often there's a small directional antenna like a horn, a variety of types that we'll learn about later, that radiates up to this reflector and can either send or receive the signal from the surface of the Earth. So that's a spinner, like one shape. You've probably seen that before in schematics or pictures of satellites. Another one that is very common is a three-axis stabilized. And this is your classical box with solar cells, solar panels sticking out of it. These are movable joints so that the solar cells can be oriented towards the sun. And so your control systems go inside the box, as well as a unit that has momentum wheels. Now this spin up or spin down depending on how you want to orient the spacecraft. Keep in mind that it's part of the spacecraft pointing towards the Earth. And if I wanted to, let's say it was an equatorial low Earth orbit, and I gave it just enough spin so that its rotation was one sidereal day. And so therefore it would be sort of phase locked with the Earth as well. It would rotate almost as fast as it would, well, exactly as fast in theory as it would go around the Earth. However, over the course of many orbits, errors would build up, and eventually the thing would be pointing off into space. We always need some sort of way to do attitude control and to have a dynamic system, one that can sense and then adjust the attitude of the spacecraft depending on the current state. So we need to tilt a little to the left or to the right. And so for that reason, we have these momentum wheels on board. You need at least 3 to do 3-axis stabilization. Most spacecraft have at least 4, because if one of the mechanical components would fail, the control system can adapt and just use the remaining 3 momentum wheels to spin up or spin down into orientation control. And so these two types kind of account for the different bodies that you see on spacecraft. There are some sets of spacecraft, especially in the world of very small seeker satellites, where really the bottom is not here. You just let the thing tumble around up there. For example, there's a whole class of satellites called CubeSats. This was pioneered about 15 years ago as a way to do very inexpensive launches with a standardized shape of the satellite. So a CubeSat, if you ever hear anybody use that term, you have a 1 cube CubeSat. You basically have a satellite that will fit in this 10 by 10 by 10 centimeter cube. And this is a convenient form factor that can stow away as a payload when a much larger satellite launch. And thereby it reduces the cost of the launch of a satellite. And so the electronics nowadays are getting so compact and power efficient and very. As you can do a lot, you need a square, what is this, a liter? You know, liter of electronics, and you can do quite a bit of sensing communications. And you can squirrel it away, and the launches are typically about $100,000, pennies on the dollar compared to the launch cost of most satellites. And so you're sitting in the standard form factor is particularly nice because, you know, you have these CubeSat launchers that are one payloads now where you can dump a bunch of these into the standard geometry and launch them. There are some satellites that you can kind of, it's almost like Legos, right? You can actually make a satellite that's 1 cube by 3 cubes, 1 by 1 by 3, or use some variant of the CubeSat architecture, so just if you're multiple, to make a slightly larger satellite if you need the available space. But there's a whole class of satellites that's gained quite a bit of popularity. Students can build these, and if you're rattle the same commonality, you can get it launched on a larger space mission. In fact, today I'm pretty sure that this year I'm going to do a CubeSat-based project